Hello, I'm Hwang from Seoul National University. Today, I will talk about Z-LFS, a zoned namespace-tailored log-structured file system for commodity small zone ZNS SSDs. ZNS SSD is a new type of SSD that follows the ZNS interface. In contrast to legacy SSDs, the space of a ZNS SSD is divided into fixed size zones. Data must be written sequentially within each zone. In addition, the host can write data to multiple zones in parallel. Zones where writes are currently allowed are referred as active zones. ZNS SSDs have two main constraints. The first is sequential write constraint, which requires data within a zone to be written sequentially. Once written, a zone must be explicitly reset before reusing. The second is the active zone constraint, which limits the maximum number of active zones. Consequently, the number of parallel write streams is restricted and cannot exceed this limit. ZNS SSD are naturally suited for log-structured file systems since they write data in append-only manner. For example, FTFS, a commonly used Z-LFS, supports ZNS SSDs. However, FTFS faces some issues when used with ZNS SSD. These include the need for an additional conventional namespace, or CNS SSD, and the underutilization of small zone ZNS SSD. These issues mainly stem from FTFS legacy design based on ZNS SSD. FTFS stores LFS metadata on a fixed location and updates them in place. By doing so, it can avoid update propagation of metadata. This mitigates write amplification and simplifies metadata management. This design is worked well on ZNS SSD, which enable random and in-place writes. However, on ZNS SSD, the legacy design violates its sequential write constraint. FTFS solves this by using an additional ZNS SSD to store metadata. This can increase cost of a storage system. The other issue is underutilization of small zone ZNS SSD. ZNS SSDs are classified based on the size of each zone. Those with small zones have fine-grained mapping between zone and SSD internal resources, such as dies and channels. Also, it has more maximum number of active zones, which means more parallel write streams. For example, the left side of the figure shows small zone mapping. A zone is mapped within a die and a channel, and the device opens more write stream for the host. In contrast, a larger size zone have coarse-grained mapping with less write streams. Due to the fine-grained mapping, the less utilization of active zones means the less utilization of internal resources in the device. The figure of upper side shows the impact of active zone utilization on I/O performance. As more zones are used for I/O, read and write performance improve. This represents that active zones utilization or zone level parallelism significantly impact I/O performance. Furthermore, even with the high utilization of active zones, using zones mapped to overlap the resources can decrease performance. The other figure shows read performance when reading data from two zones in parallel. Compared to no conflict scenario, performance with channel level and die level conflict is reduced by about 20 and 50% respectively. However, the data placement strategy in FTFS does not consider these aspects. FTFS logs data and node in 6 log streams and allocates only one active zone per log stream at a time. This approach reduces active zones utilization. Furthermore, it is unaware of the fine-grained mapping of small zone. As a result, it may select zones that share the same internal resources, leading to resource conflicts. Consequently, internal resources are underutilized and the performance of F2FS is degraded. Addressing these issues is not straightforward. First, a naive append-only approach to metadata management can increase write amplification. Second, simply distributing an equal number of active zones is insufficient to fully utilize them. Due to the active zone constraint, a file system cannot optimally allocate the same number of active zones to all log streams. In addition, because the write intensity of each log stream depends on the workload, the optimal number of active zones for a log stream cannot be determined statically. Finally, to avoid resource conflicts, the file system should be aware of the zone mapping and manage it accordingly. To address these issues, we propose Z-LFS. Z-LFS enables a ZNS SSD to be used as a standalone storage device while minimizing write amplification. It also minimizes the resource utilization of small zone ZNS SSDs. For broader applicability and compatibility, Z-LFS is implemented entirely in software and target commodity small zone ZNS SSDs. Z-LFS introduces three key design elements: append-only metadata management, speculative log stream management, and conflict-aware zone allocation. For write operations, data and nodes are classified into one of 6 log streams based on their temperature and type. Z-LFS dynamically adjusts the number of active zones assigned to each log streams according to each write intensity. A superzone is a group of zones, and writes to a superzone are distributed across each zones. By allocating or deallocating superzones, Z-LFS adjusts the number of active zones for log streams, thereby increasing overall active zone utilization. Meanwhile, Z-LFS classifies metadata into mutable and immutable types based on their life cycle. These are managed in distinct ways to enable efficient append-only metadata handling. Data, node, and immutable metadata are stored in main area, while mutable metadata are logged in delta log area, later merged into merge area. For append-only metadata management, Z-LFS leverages the unique characteristics of LFS metadata on ZNS SSD. In LFSs on ZNS SSD, write operations on a segment are not strictly sequential due to various optimizations. As a result, metadata in such systems have a life cycle that differs from that of their corresponding segments. However, in LFS on ZNS SSD, write operations must be strictly sequential. Consequently, some metadata share the same life cycle as their associated segment. One representative example is the reverse mapping of data blocks. As shown in the figure, when data is logged to a segment, each parent node or inode stores the location of the data block. The reverse mapping is also recorded and later used to locate the parent inode from a data block during GC. On a ZNS SSD, when a block in a segment is invalidated, the file system can overwrite it with new data. In that case, the reverse mapping must be updated accordingly. However, on a ZNS SSD, blocks are never overwritten, and thus reverse mapping remains unchanged until the entire segment is cleaned. With this insight, Z-LFS classifies metadata into immutable and mutable types. Immutable metadata shares the same life cycle as their corresponding segments and are never updated once written. Therefore, Z-LFS append them to the end of their corresponding segment. In contrast, mutable metadata do not share the segment life cycle and can be updated after being written. Z-LFS logs them in dedicated areas. For mutable metadata, Z-LFS logs only deltas, which are the modified entries of the metadata. These logs are written to a fixed delta log area so that their location do not need to be tracked. To reclaim space in the delta log area, Z-LFS collects the logs and merges them into the full metadata table in merge area. This cleaning operation is triggered when a portion of the delta log area becomes full and is performed in background to minimize overhead. To increase active zone utilization, Z-LFS adjusts the number of active zones allocated to each log streams. It first determines the optimal number of active zones for each stream based on each write intensity and dynamically scales active zone accordingly. Specifically, the number of active zones assigned to log stream I is calculated by multiplying the total number of available active zones by the ratio of write requests to stream I over the total write requests. Z-LFS avoids both channel and die level conflicts by managing superzones and interference groups, or IGs. Superzone is a group of consecutive zones that do not overlap at the channel level. By striping data across zones within a superzone, Z-LFS avoids channel level conflicts. IG is a set of superzones mapped to the same dies. Routing to superzones from different IGs helps avoid die level conflict. Z-LFS allocates active zones in units of superzones. It prioritizes superzones from non-overlapping IGs to reduce die level conflict. Writes to a segment within a superzone are distributed across each zones. As a result, sequential writes and reads to the segment can leverage zone-level parallelism more effectively. For the evaluation, we used commodity small zone ZNS SSD with 96 MB zone size. The maximum number of active zone is 384. We compared Z-LFS with vanilla F2FS and F2FS with static striping, where each log stream is allocated 64 active zones equally. We also evaluate eZNS, a state-of-the-art interface for commodity small zone ZNS SSD that aims to maximize active zone utilization. eZNS is tested with and without F2FS. Note that all techniques with F2FS employ an additional SSD to store LFS metadata. In micro benchmark, to evaluate write throughput, 16 FIU threads sequentially or randomly write to dedicated files. We use buffered I/O for approaches with F2FS and direct I/O mode for others. Compared with F2FS with static striping, Z-LFS achieves up to 37% higher throughput thanks to better resource utilization. Furthermore, Z-LFS outperforms eZNS with F2FS. While eZNS alone can achieve high write performance, each combination with F2FS results in suboptimal performance. This is because eZNS lacks cross-layer awareness and F2FS provides only limited active zone utilization. Specifically, eZNS does not consider the write intensity of each log stream and allocate a nearly equal number of active zones to all streams. As a result, eZNS with F2FS fails to fully utilize the resources of small zone ZNS SSDs. In contrast, Z-LFS is aware of write intensity log streams and allocates more active zones to those streams. This allows Z-LFS to maximize resource utilization and achieve better performance. Even in MD test, a metadata-intensive workload, Z-LFS outperforms all other approaches. In this workload, not only LFS metadata, but also node blocks are frequently updated during file creation. Thus, better zone-level parallelism improve node blocks writes and lead to higher performance. In terms of write amplification, Z-LFS shows similar level of amplification in both data and metadata intensive workload compared with F2FS. This result demonstrates that the append-only metadata management in Z-LFS can minimize metadata write amplification. We evaluated the performance in RocksDB's DBBench, a real-world key-value store benchmark. Z-LFS outperformed other approaches on the write-intensive workload by exploiting enhanced zone-level parallelism, while maintaining comparable read performance without incurring noticeable overhead. In conclusion, there are two major issues with using LFS on small zone ZNS SSDs: the need for an additional ZNS SSD and the low resource utilization of ZNS SSD. As a LFS for commodity small zone ZNS SSD, Z-LFS successfully addresses the issues with three key design elements. Thank you for your listening.